Okay, so this problem is very similar to the CPD 16 and 17. We're going to try to prove part of theorem 141. In particular, part of theorem 141 says if you have two vectors, then the sign of that little determinant gives you tells you information about whether it's whether it's clockwise or counterclockwise order. But the area of the parallelogram is computed as the absolute value of that determinant. Right, so that's the part we're going to be proving here. So we're going to, let me write this down. What we're trying to show here is that the area of the parallelogram defined by V and W is equal to the absolute value of the determinant of that little matrix V1, V2, W1, W2. Okay. Okay, so first step is to observe that if you have these two vectors in R2, V and W, the area of that parallelogram is the same as the area of a corresponding parallelogram in R3. Namely, I could look at this vector here, which is V1, V2, 0, and I can look at this vector here, which is W1, W2, 0, and I can form that sort of same, well, it's not exactly the same, but it's very similar little parallelogram. Right, so geometrically speaking, I'm just going to appeal to your geometric intuition that the angle between those two vectors is the same as the angle between those two. All I did is I took these two vectors and I sort of just physically picked them up and sort of placed them down in the xy plane in R3, and I claim these are effectively the same parallelogram, even though of course this one's in R2 and this one's in R3. So are you all geometrically willing to believe that these have the same areas? Because they're pretty much the same parallelogram? Okay. All right. So now I know. So let's call this A, by the way. So I know that the area that I'm looking for is the same as that, and I know how to compute this area. The area of that parallelogram is the length of the cross product. So we have this, this is the other theorem that's referred to here. The exercise says use theorem 1.4.4. Theorem 1.4.4 says that the area of this parallelogram is the length of the cross product of these two vectors. So let's compute the length of that cross product. It's V1, V2, 0 cross W1, W2, 0. Well, I got to compute the cross product first. So let's see, the first component is 0. The second component is 0. And the third, again, computing the cross product, the third component is V1, W2 minus V2, W1.
Did you just do that in your head, or did you not use the E?
There is no E in this stage of the problem. All we're doing is computing the cross product. Oh, I'm sorry, the little determinant trick. Yeah, right. Yeah, kind of. I mean, you're going to notice after you've done a zillion of these that when you're taking a cross product of two vectors that are written as columns, the first element is that times that minus that times that. And that times that is 0. That times that is 0, so therefore 0. And the second one is that times that minus that times that, again 0. Yeah. And then the third element of the cross product is that times that minus that times that, and that's this thing here.
Okay.
Yeah, it's just, it's don't be impressed. Nothing impressive. Yeah. You just start to notice these patterns. Okay, now we got to compute the length of this vector. Now that's the square root of the sum of the squares of these coordinates, but the square root of the sum of the squares, well, these are zeros. It's just the square root of this squared. In other words, it's the absolute value of that, which of course is just the absolute value.
It's off the screen.
Oh, I'm sorry. Thank you. It's just the absolute value of, again, that's a little 2 by 2 determinant. And that's what we were supposed to show. So the
Can you explain that step one more time?
area. The what now? From where to where?
The
From here to here?
No, one more.
From here to here?
Correct.
Yeah, okay. So got a length of a vector. The length is the square root of the sum of the squares. Right? So it's going to be the square root of that squared plus that squared plus that squared. Well, these are zeros. So it's just going to be the square root of this squared. And remember, there's a fact of algebra, good thing to make sure everybody's familiar with. When you take some number and square it and then take the square root, you do not necessarily get the same thing back. What you get back is the absolute value of that thing.
Right.
Right. Because this little symbol here means positive.
Oh, so you're just going the reverse direction.
I'm sorry?
So you're going the reverse direction from the length to the... Like usually we take that and find the length.
Take this here?
Yeah.
Yeah, no, that's in fact exactly what I'm doing. Let me. I sort of skipped a step. Let me fill in the blank. This is the square root of 0 squared plus 0 squared plus, this stuff in there squared. This is V1 W2 minus V2 W1. So of course that goes away. That goes away. I have the square root of the square of something, which is the absolute value of that thing. Yep. Yep. Is everybody good?